good morning, everyone. And yes, I'm going to pretty much talk about a work that we've been doing in collaboration with the University of Calabria. In reality, the presentation is split in three parts. The first part is the research done by Luciano and Pietro Mazzucca, and then I will show you research that we actually did at the University of Canterbury, which was my former university before I moved to San Diego. So the first part will be more looking at what are the benefits of combining FRP with steel reinforcement in terms of serviceability. And this is really the part that is research conducted by Luciano Ombres and his team. And then I will talk about the research that we conducted at the University of Canterbury in New Zealand, and then I will show you some future projects that we have on. Now, I think we are all familiar with the properties and the combination of the materials. As you can see here, right? We have a pure elastic, and then we have the typical steel beam in terms of moment curvature. If you start combining the two, depending on the contribution of reinforcement, you will either tend to go, depending on how much you put, you either tend to go in the steel or you go in the FRP. Now, what you have as a main difference is that by doing an hybrid, you will have a compromise, you will have a better stiffness, and also another important aspect is the post-yielding stiffness. Now, in terms of earthquake application, we always think about ductility, and I will show you what, based on the research that we did, for us, overall, is certainly the initial stiffness is very critical, but the post-yielding stiffness play a very crucial role in terms of also improving the performance in terms of under earthquake loading. Now, in the first part, basically, I will go very quickly because I want to talk more about what I did, and I know that we have a limited time. In the first part, basically, Luciano and Pietro, they looked at different testing, and I will show you a couple of slides where they were conducted a lot of tests on beams and with different reinforcing contribution in terms of FRP and steel bars. And the idea is that taking those tests, then they want to compile a large database and then verify and possibly improve the formulations, especially for the assessing the cracking stiffness and for predicting the deflections and serviceability. Now, this was a work done by Luciano more than 20 years ago, where basically you can see if you use a just B1 is a typical steel beam and B2 is only GFRP, and then what you can see is that the combination of the FRP with steel can improve the overall performance. Now, what we have to consider here is this, that in this particular aspect, if you look the A2, A1, A3, it's not just the amount of reinforcement, but also is the position of the diameter. So you can basically play in a way that you want to reach the maximum curvature and at each reach the balance failure, right? That will be the best in terms also of achieving the maximum ductility. And so, but then obviously, there been other research, and this was part of the database that we've been compiling, where, like in this research, where we have pretty much the beams, and you have different reinforcement ratio, different contribution between the GFRP and the steel, but in this particular case, they kept the bars at the same layer. So therefore, you will have one of the two becoming the governing strain, and therefore you will be very difficult to have a balanced curvature where you trigger, the failure of all the three materials because they place the bars in the same layer. And so you can see here that obviously if you increase the effective ratio, reinforcement ratio, which combines the two materials, you will increase, this is using the GFRP, you will obviously increase the strength and the moment capacity, and in terms of deflection, there is not a big difference. And this is again because in this particular case, the reinforcement has been not placed on the same layer. And then there is research done by Baltimore Crane and other authors. It was a collaborative effort that, of course, we can play and we can improve, if we wish, the ductility of the system by also changing the mechanical properties of the concrete. This is the use of a geopolymer. I mean, the geopolymer has a different nature because in a way, if you look at the single stress strain curve, you have a very good post-peak softening, so you don't have, and therefore, what happened is that when we're looking at these, they could, they did the test, they could see that you have an overall more ductile failure because the governing material crushing was of the concrete, and therefore you have a better, because of the better post-peak, you have overall a better performance. Now, what Luciano and Pietro did, they pretty much collected 126 of those beams, and they looked, these are the parameters they included. And I will show you a couple of slides. They then plotted the strength, the deflections, and the ductility. And when I was looking at those data, I couldn't find really good correlation, I have to be honest. So I mean, you can see here, and I think, as I was mentioning before, there are, this is like the moment versus the concrete strength, the moment versus the ratio between the steel and the FRP, and then you have the effective ratio. And I think, as I said, I think probably we need to slice in more this database and do regrouping in terms of collocation of the reinforcement, diameter of the bars, and probably there will be better trends. The only good trend that I found is actually the ductility, but this is something that we know. If we increase the reinforcement ratio, the effective reinforcement ratio, we know that the ductility is dropping. So, and this is also the other, so I think there is, overall, it's valuable actually to have this database and possibly to use, I mean, in the earthquake space, we use Design Safe with part of NERI, where you can actually post the database. They also accept a non-seismic database, and then there will be even a ISBN code associated. So therefore, this is quite useful then if the research community can use it. Now we move to the second part, which is really the part that I worked on, which is pretty much a work that was triggered by the Kaikoura earthquakes. We have, when I was in New Zealand, I've been lucky to went through 4 earthquakes, and I mean, depends how you see it, but professionally, I was very lucky. As a citizen, no, but exactly, I didn't, I had a lot of issues with my house though, but we have, this is an example of a plastic hinge happened during the Kaikoura earthquake, and that an example of typical corroded bridge pier. Most of the infrastructure in New Zealand are along the coastline. So we're collaborating with Pultrons, with Peter, and we say, okay, what do we do? And so then the first thing I say, okay, I didn't have a lot of experience on the material. I say, okay, what I want to do, I will put, this is the capacity chain, part 1 increase. They say, we put the material on the capacity protected element, in the elastic rings, not in the ductile member, because I want to want to use a steel. But then, from the earthquakes, we actually learned that ductility is not enough. I mean, you have to look at the post-earthquake repairability, and you have to think about resilience, right? So then with discussion and thinking, we say, hey, let's actually try to think how to use the material within actually a dissipative element in a potential plastic hinge of the column. And so this is the benchmark. Then the hybrid that we did, which is different than what I was referring before, in this particular project, we actually looked at using the spirals with GFRP, but we used a steel reinforcement, and then we wanted to do a full GFRP column. So the solution number 2 is more to improve the durability, right? Because you will have usually corrosion attacking the stirrups first. the solution number 3 was to try to look at a full recentering system, because what we found is that very important is for earthquake performance also to have the ability to the structure to recenter and go back to the original position. So we tested 6 specimens for this campaign. So we did quasi-static cyclic test, and you can see that we didn't use a concrete footing. We used this steel footing, which was bolted with 2 halves. The reason because I had other 2 PhDs, and we tested other 20 columns, and by not casting the footing was a big saving. Obviously, we monitored all the displacements because we want to make sure that there is no slip between the grout and the footing. And we tested, we looked at the hybrid, we changed the spacing, we kept the spacing with the benchmark, the same spacing, and then we increased the diameter of the bars, and then this is the full GFRP. Now, obviously there's been a lot other work done, especially by the Canadians, but this was detailing with the New Zealand standards. And then I believe that this is actually one of the largest tests. We went almost close to 2 feet diameter. And so, as you can see here, if we compare the conventional with the GFRP spiral, you have the benefit. You can see that the post-peak is slightly better, if you look. And then you have a little bit larger loops. And the reason is because if we look also the damage, plastic hinging, 350, this is millimeters, so 14 inches, yeah. And the same as here. What you can see is that you have less buckling of the bars. So the reason is that is pretty simple, because when you have your steel spirals, right, you go beyond the yielding, they yield, you lose the confinement. While what we did here, especially with the bars, that we increased the diameter, not the one that had the same diameter, so we increased a little bit the stiffness of the rope, and here we have a far better performance because you have a consistent, elastic confinement that actually kept the structure, the longitudinal bar in place. So then we compare, let me see. Then we compare the benchmark with the full GFRP. Now, when we're looking at these, obviously, and you will certainly say, oh, look at that. This is a terrible loop, hysteresis, because you have pretty much very minimal energy dissipation. So probably this is, if you look at the accumulated energy dissipation, I'll show you later, is 30% of the benchmark. But there is an advantage that is that the post-steel stiffness is ascending and not descending, and then you have the recentering. So if you look at the test, now what happened, because they've been designed at 30% of their ultimate strength, right, due to the sustained load, you will see that if you keep loading, right, here you have a plastic hinge, which were 14 inches. The plastic hinge developing here is 3 times more, because the bar keeps picking up. Now you will say this is bad, right, because you have more damage. I agree with you, but it's also positive because the material is elastic. So after the earthquake, technically, we have just to patch the surrounding. So it's a sort of elastic hinge, if you wish. So I'm not saying this is the solution because you say, oh, we need to dissipate the energy. But what I'm just showing is that there were surprises. I mean, it was actually good, yes. What I want just to show you is that having an ascending branch is quite positive in a way, because if we put those two specimens on the shake table, I can guarantee that the displacement demand will not be 3 times more, because we have 30% of the energy dissipation. That post-yielding and recentering is probably giving 20-30% more displacement demand. So this is quite positive. So ductility is important, but we have to think that there are other parameters. The recenter is also very important. So this is pretty much the summary. The energy accumulated is clear. And obviously, what we have is that the initial stiffness is lower if you have a full GFRP. Therefore, you have a higher yielding displacement. Because we stopped the test at 6% drift, so we have also a lower ductility. But we didn't actually push the specimen to failure. Now, opening, I know that I almost finished, Celeste. So if we think about go back capacity design, all the Poly and Priestley book, plastic hinge, how do we define the plastic hinge in those systems, right? Even if we go with hybrid, because we have this K factor. Then strain penetration. We are talking about large diameter bars and these high tensile stresses. They will be a new formula. We can't really use the formulation that is developed for the steel bars. So there is a lot of work to do. And I will skip the conclusions. I mean, we went through pretty much a lot, but I want to, okay, yes. All right, thank you. So you were putting me pressure, so I was getting anxious. So I mean, conclusion, I think, I would say that, and I will show you what we are planning to do. I think we may not go directly, especially considering that we've been designing with steel, right, in plastic hinges in the seismic. You will not go directly to the full GFRP. But that was the extreme, right? We want to have that extreme, and we have the benchmark. So in conclusion, I think even based on the research done by Luciano and Pietro, I think the idea is to try to combine the two materials, because then we can have a little bit of dissipation and the recentering coming from the GFRP. So I want to acknowledge Caltrans and Peter and the student Kane, amazing PhD student at the University of Canterbury, because they've been amazing with me for 12 years, 13 years. I'm actually Miss the University of Canterbury. It's not that I don't like UCSD, but they've been very good. Now, just to close, the future is green, pink, whatever, depending on how you look, right, the producers. What we have, the good news is that Caltrans, we have a project that's been awarded, is starting in 26, where we are looking at developing guidelines for hybrid bridge piers, and will be also with the University of Miami, with in particular with Antonio Nanni. And the idea is to do some cyclic tests on large scale, diameter. And here I also propose the idea of actually debonding the GFRP and debonding the steel, because we have done similar testing for rocking structures. So the idea is to activate rocking. And eventually, if we have some funding, or we want to join the effort, we can use the Ferrari of the shake table, which is the UCSD. Where Professor Restrepo tested this massive pier in 2010. I'm actually writing a proposal for Friday on something similar for ABC. And if the proposal gets funded, maybe you guys all together, we can try to get more funding and have just a test on hybrid or full GFRP. Because I think we need those large-scale testing. Because I think it's the only way to convince the industry, and especially the DOTs, that we can use this material in seismic applications. Thank you very much. And there is this conference in Girona. You probably are aware, FRP, RCS. We have a session, so please try to join the session. All right. Thank you.
Any questions?